Welcome to my talk about restoring eutrophic lakes with an lanthanum modified clay. My name is Said Yasseri and I'm from the Institut Dr Nowak. My institute is located in northern Germany near Bremen, and we are involved in many restoration projects, and we have a lot of experience about precipitation of nutrients from the lake water body. And I will show you some examples in my talk now. First, I give an introduction about eutrophication and measures against eutrophication. Second, I present some examples of lakes that we had treated with Phoslock. I show the lake characteristics and the result of the Phoslock treatment. And after this, I show you some investigations on sediment that we had done in a lake near Hamburg, and I show the lake characteristics and the difficulties that we had with this. I compare the Phoslock capping with the phosphorus that is available, and I show the results from this project and show some further strategies, and at last I give some conclusions. First, we have to find out where the sources of nutrients are coming from. There are external sources, maybe from stormwater, discharges, streams or rivers, or there are internal sources from groundwater and sediment. And measures against these external sources are the reduction of nutrient inputs, of course. We can upgrade sewage plant steps. We can create buffer zones or artificial wetlands to reduce the nutrient inflow, or we can renaturalize rivers that are flowing into these into lakes or water bodies. For to reduce internal sources, we can restore the sediment. As an internal measure, we can do as well biomanipulation, maybe, to remove fish, especially carps that can dig in the ground. We can plant macrophytes that will stabilize the sediment and reduce the turbidity in the water body. We can add mussels as a filtration system. In many cases as well, there are, on the technical side, there are installed aeration or desertification systems that has good effect on the oxygen concentration in the water body, but a limited effect on the binding of phosphorus sediment. To reduce or to make up the sediment, you can use alum or iron that are flocculants that can flocculate particles and anions like phosphate, but there's always an overdose required. That has an effect on the water body in conductivity and pH. The P binding depends for iron on the oxygen concentration in the water body and sediment, and for alum and aluminium chloride, the pH it must be proper. With alum, there's a big problem because you will add sulfate as well, and sulfate is an bacterial nutrient, and that can create reductive conditions because the bacteria uses the sulfate and reduce it to a sulfide. Sulfide is a very strong binder with iron and will block the iron, so the iron can't bind no phosphate anymore. We can use calcium. Calcium is a strong phosphate binder, but for an application, it's very tricky. You need very proper conditions, maybe a pH of 8.2. And as well, you can use Phoslock as a lanthanum modified clay, as have very low influence on conductivity and pH of the water body. It's bind phosphate within a wide pH range, and you can condition the sediment, make it sediment able to bind the phosphate. And the disadvantage of the Phoslock is maybe that other anions like carbonate can compete with phosphate. What is Phoslock? Phoslock is a bentonite. It's a special kind of bentonite, a montmorillonite, and that are layers, and within the layers, the sodium cations are exchanged with lanthanum cations. The maximum load with lanthanum is 5%. And the binding characteristic of lanthanum is 1:1 against phosphate. 1 mole of lanthanum can bind 1 mole of phosphate. Our lab tests have shown that 1 ton of Phoslock can bind 11 kilograms of phosphorus. And it has, as I said before, a wide binding capacity within a wide pH range. How to apply Phoslock? Phoslock delivered as a dry granule, and it has to mixed with water, lake water on site, and this slurry is sprayed out over the water surface or injected into the depths. We use different kind of barges, pontons, floats to spray it out, and all these applications are GPS controlled to create an equal cover of the sediment. In my first example, I show a project that we had done, the Behlendorfer See. It's located in northern Germany, in Schleswig-Holstein. It has an area of 63 hectares and a depth of maximum depth of 16 meters. It's a natural lake, and the external sources are reduced by before our precipitation measures. It has a small catchment area, and maybe some groundwater can enter this water body. The internal sources are big. The sediment carries 1,400 milligrams phosphorus per kilogram dry weight, that are around 1,600 kilograms releasable phosphorus in the first 5 centimeters. Before we restore, 2 years before we restore, we have measured 320 micrograms total phosphorus per liter lake water, that are around 1,250 kilograms total phosphorus per liter in the whole water body. That has led in cyanobacterial blooms, low visibility, and of course no macrophyte growth. How to calculate the right dose of Phoslock is that we have measured the water body, the concentration in the water body, and found out there are 550 kilograms of phosphorus in the water body that has to be bound. And in the sediment, there was 1,590 kilograms that is easily releasable or available for the biology in the water body. In total, it was 2,140 kilograms, and that requires 214 tons of Phoslock to precipitate the material, the phosphorus. The results have shown a nice reduction of phosphate and phosphorus in the water body. The phosphorus level dropped from 90 to below 30 micrograms per liter till now, from the application till now. We had a very low reduction in total nitrogen, not very significantly. That means that we have still biomass in the water body, and maybe a small reduction on ammonium. That means we have a slight lower bacterial activity in the water body. But because of the better transparency in the water body, we have that we have a good macrophyte growth, and the better transparency is a result of the chlorophyll reduction. That means we have smaller phytoplankton biomass in the water body. And the lanthanum concentration decreased bit by bit over the month till lower than 10 micrograms now. In our second example, the Bärensee, it's an artificial lake, a small lake, 6 hectares in size, a maximum depth of 3.8 meters. It's a not stratified lake. It's located within the biggest camping site in Hessen, that's in the middle of Germany. We have external and internal sources as well. External sources are groundwater runoffs, but swimmers as well. There are in the year more than 3,000 swimmers per day, and each swimmer can bring in to the lake 94 milligrams phosphorus per day. That's a very important source for phosphate and nutrient in the small water body. The internal sources is the sediment as well. The sediment has 700 milligram total phosphorus per kilogram dry weight, and that means in the first 4 centimeters we have 93 kilograms releasable phosphorus. The concentration before our restoration project started in the water body was 90 micrograms total phosphorus per lake water. That are only 14 kilograms total phosphorus for the small water body, but the problems are by cyanobacterial blooms and a very low visibility of lower than 50 centimeters and swimming bans. The results of our application show that we have a nice reduction of phosphate and phosphorus. That's a different kind of measure that we did there. We had an initial dose of 11.5 tons of Phoslock, and we reduced it to the phosphorus concentration in the water body to 30 micrograms. But because of the external source like swimmers, we had to add after 3 years again a smaller dose of 3 tons, and after again 3 years an additional dose of 4 tons to keep the phosphorus concentration below 40 micrograms. We had as well a nice reduction in total nitrogen. That means we have a lower biomass in this lake, and that shows as well that the ammonium concentrations are very low now, and that means that we have lower bacterial activity in the lake as too. That leads in better transparency and lower chlorophyll concentration. We have a smaller algae growth in the water body. The lanthanum concentration dropped very quickly after the application and are below 10 micrograms. The next project, that's the lake in Hamburg, where we have some study on the sediment of the lake after Phoslock treatment. This lake is an artificial lake as well as a recreational lake in Hamburg, and his area is 23 hectares, and this maximum depth of 60 meters. We have external sources like swimmers and groundwater and runoffs, but we have a very, very big internal source. The sediment contains 1 gram, more than 1 gram total phosphorus per kilogram dry weight. That means more than 950 kilograms phosphorus is releasable. Before we restored, we had 560 micrograms total phosphorus per liter lake water. That are almost 1 ton of total phosphorus in the water body. And that leads, of course, in strong cyanobacterial blooms and a very low visibility and swimming bans. Yeah, this lake has a long restoring history. In the beginning, it was this lake was destratified, but that can't hinder that the phosphorus concentration increased. And they started in alum precipitation with 115 tons of alum, and to get a reduction of phosphorus, that was happened only half a year, and then the phosphorus concentration increased as well. They installed a first hyperlinic aeration system, the second one, but they can't remove the phosphorus concentration in the water body. The phosphorus concentration increased and increased. Finally, they switched it off, and very high amount of phosphorus came free. That was in 2010, nearly 1 ton of phosphorus that was released in the water body. We carried out a Phoslock application in late 2010 and had a reduction from 1 ton to 50 kilograms. But during the following summers, we had additional phosphorus in the water body, in the deep water areas of the water body. We added some small amounts of Phoslock to reduce these additional phosphorus. And the question was, where does this phosphorus coming from? Is it an external source, or is it an internal source that is responsible for the additional phosphorus? Because to find out what the reason are, we have taken cores from different sides of the lakes, and we sliced each core in 2 centimeters layers and measured in each layer phosphorus and lanthanum to compare, to find out if they have added the right dose of Phoslock to bind all the phosphorus that is available or maybe releasable from the sediment and deeper parts of the sediment. To show it more clearly, I created graphs with the shape of the lake and the different layers to make it more clear where the phosphorus, where the problem is located in the lake sediment. And you can clearly see that we have a lot of phosphorus in the first 2 layers, that means 4 centimeters, but we have as well in the deeper areas phosphorus as well. And so maybe more phosphorus from deeper areas is available and interact with the water body. And compared to our lanthanum dose, we can see that the lanthanum concentration in these sediment layers are smaller than maybe necessary. To make it more clear, I paired both made a ratio between phosphorus and lanthanum, and to find out where the problems are. And you can clearly see that we had a cover of lanthanum to bind the releasable phosphate, but it's a very small cover and maybe not enough. And finally, we found out we had an underdose to bind all the phosphate that is available from the sediment. And that had led finally to a new strategy to inject the Phoslock over the sediment to create an equal cover to bind all the phosphate and keep it back to the sediment. In our conclusion, we can create a good reduction in phosphorus concentration with Phoslock. We have a rapid and permanently binding to lanthanum and can create a long-term pee removal. We create a better transparency, and that leads into macrophyte growth, and that will improve the oxygen profile. And the investigations on the sediment on phosphorus reduction shows that that deeper sediment resource can be available, and wind drift or currents during the application can have an effect on the distribution of Phoslock. And we developed a new injection strategy to add Phoslock on the right positions in the lake. Okay, I'm now finished, and I thank you for listening my talk. And this last slide shows where I come from. Thank you very much for listening to my talk. Thank you.